If we have the graph of a function, we can shift it along the x-axis in the negative direction or in the positive direction. So here we have the graph of y equals x squared, and if we shift it 3 units in the negative x direction, it looks like this, and if we shift it 3 units in the positive x direction, it looks like this. And the question here is, how do we work out what are the equations of the shifted graphs? Because they are certainly not going to be defined by the formula y equals x squared anymore. Now, in fact, we can find the equations of the new graphs by thinking about what happens to the x-axis. Given an image like this, we would probably create a y-axis like this, because usually the minimum of the square function corresponds to the origin of our axis system. Correspondingly, we would number the x-axis like this, but now we get a surprise because we notice that someone has already created a y-axis like this, and they have numbered the x-axis like this, as we would expect, and in fact they choose the letter x to name their x-axis. Now, since someone else has already used the letter x for the horizontal axis, we choose the letter u to name our axis. And so our axis system is the uy axis system. The other axis system is the xy axis system. Now we can see that the u values are always 3 less than the x values. That means that u equals x minus 3 for all values of x. In our u-axis system, the graph has equation y equals u squared, and we know that u equals x minus 3, so that u squared equals x minus 3 squared. And so we find that in the x-axis system, the graph has the equation y equals x minus 3 squared. And so we can write the equation for one of the graphs shown earlier. If we take y equals x squared and shift the graph 3 units in the positive x direction, it has equation y equals x minus 3 squared. But this looks strange, doesn't it? Because we moved the graph plus 3 units along the x-axis, but we subtracted 3 from x. What's going on? After all, if we're subtracting 3, shouldn't something be moving in the negative x direction? Well, it turns out that something is indeed moving in the negative x direction, and we've already seen what it is. It is the axis system, as we can see illustrated in this animation. We can see that when we replace x with x minus 3, we shift the axis system 3 units in the negative direction, but we hold the graph of the function still. We should note that the discussion above does not depend in any way on the function y equals x squared itself, and that's because to translate a function, we make no changes to the function, rather we change the axes. And so if we make the transformation x to x minus 3 in any function at all, we shift it 3 units to the right, i.e. 3 units in the positive direction, as we can see in this example. And so we can now interpret the instruction x goes to x minus 3. Literally, it means replace all instances of x in the equation for f of x with x minus 3. Graphically, it means create a new x-axis, shifted 3 units in the negative x direction while holding the graph stationary. And we should note that the fact that we shift the graph in the negative x direction corresponds to the fact that we subtract 3 from x. We can use exactly the same argument when we shift the function in the negative x direction by 3 units. In the formula, we substitute x with x plus 3, and graphically, we shift the x-axis in the positive direction by 3 units, holding the graph stationary. And we can note that the direction of shift of the x-axis in the positive direction is consistent with the fact that we add 3 to x. It's important to note, of course, that it makes no difference if we think of moving the graph 3 units in the negative direction, or if we think of moving the axis system 3 units in the positive direction. These are entirely equivalent points of view. On the other hand, algebraically, we substitute x with x plus 3, and the x in those formulae refers directly to the x-axis, and the x plus 3 is consistent with the direction of movement of the axis. So it's less confusing to think about the movement of the axis than the movement of the graph. We can also translate a graph along the y-axis. So for example, if we translate the graph of y equals x squared 3 units up the y-axis, then what is the equation of the new function? So here we see the graph of some function, with the axes chosen so that the minimum of the function is at 0 on the vertical axis. Here we have a shifted vertical axis, where the 3 on the shifted axis corresponds to 0 on the original axis. We call the shifted axis y and the original axis w. And so we have an xw axis system and an xy axis system. And in the xw axis system, the graph has equation w equals f of x. Now we can see that for all values of y, w equals y minus 3. In the w-axis system, we write w equals f of x, but since w equals y minus 3, in the y-axis system, we write y minus 3 equals f of x, because w equals y minus 3. However, usually we rearrange that as y equals f of x plus 3. And note that we are treating the x-axis shift and y-axis shift consistently. We are thinking about what happens to the axes, not about what happens to the function. And of course, we can apply the same reasoning to a translation of a function 3 units down the y-axis. In this case, we find that w equals y plus 3, so that since w equals f of x, then y plus 3 equals f of x, which we rearrange as y equals f of x minus 3. When we translate a graph along the y-axis, we often write the final form in a way that disguises the change to the y-axis variable. So if we shift y equals f of x 3 units up the y-axis, we write y minus 3 equals f of x, which we usually turn into y equals f of x plus 3. However, sometimes we don't want to do that, and sometimes it's impossible to do that. So for example, the equation for a circle centre the origin with radius 2 is usually written as x squared plus y squared equals 4, and not as y equals plus or minus the square root of 4 minus x squared, where we have attempted to write the equation in the form y equals f of x. In fact, there are 2 equations in that expression, y equals the positive square root of 4 minus x squared, and y equals the negative square root of 4 minus x squared. So it's a bit of a mess. And we almost always stick to this form when writing the equation for the circle. And so if we translate this circle 3 units up the y-axis, we write x squared plus y minus 3 squared equals 4, rather than y equals plus or minus the square root of 4 minus x squared plus 3, which is a pretty unpleasant expression. Now consider the equation y to the 5 plus y cubed equals x to the 5 minus x cubed. It turns out that it's impossible to write this equation in the form y equals f of x or x equals f of y. which means that we can't write the translation of this function in the form y equals f of x plus 3. However, in fact, it's trivial to write down the equation for the translation of this function 3 units up the y-axis. It turns out to be y minus 3 to the 5 plus y minus 3 cubed equals x to the 5 minus x cubed, where we have made the transformation y goes to y minus 3. And in cases like these, it's simply impossible to disguise the fact that we are making a change to the y-axis. Now, we can describe a simultaneous translation in both the x and y directions by specifying a translation vector. So, for example, you may see a question like, translate the graph of y equals x cubed plus 1 by the vector 3 minus 2. When we translate a graph by a vector, we are adding the vector, the translation vector, to the position vector of each point on the graph. And we will discuss the effect that these translations have on the formula for the graph in the next video. Here we see animations of the two translations of the graph of y equals x squared along the x-axis that we have discussed. And the animations show the axes being held stationary and the graph itself being translated. And similarly, here we see animations of the translations of the graph of y equals x squared along the y-axis, with again the animations showing the axes held stationary and the graph being translated itself.